Okay, chemists, today we're going to talk about balancing chemical equations. Hopefully you've had some introduction to this in the past, but if not, no worries. We're going to learn all about it all over again. So a chemical reaction can be described in three ways. You can use English words, hydrogen reacts with oxygen to produce water, and turn that into a skeletal equation, H2 plus O2 equals H2O. But the problem with that skeletal equation is that you have two molecules of oxygen going in the reactant side and only one in the product side, and that can't be. Law of conservation of matter states that matter cannot be created nor destroyed. So any elements that you have going in the reactant side have to come out the product side. We cannot change the subscripts or how compounds actually occur. So what we need to do is add coefficients to balance the chemical equation. So only a properly balanced chemical equation correctly represents the reaction that's actually happening. So we're going to pick apart the different parts of the chemical reaction. So the coefficients here are going to tell us how many actual atoms, molecules, formula units, ions, or moles of a substance we have. Notice that oxygen doesn't have a coefficient. When it doesn't have a coefficient, that is one understood. So we have coefficients that multiply everything behind it until you bump into a plus or a yield sign. So the coefficients tell us that 2 molecules or 2 moles of hydrogen react with 1 mole of oxygen or 1 molecule of oxygen, 2 moles or 2 molecules of water. So this arrow in between here is the yield sign. That's kind of an equal sign between the reactants and the products. So the count of the number of atoms on the reactant side over here has to equal the count or the total of the number of atoms on the product side here always. These parentheses with the letters in it after them, after the compounds, in this case molecules, stand for the states of matter. So G is gas, L is liquid, S is solid, which is the also the term we use for a precipitate. We'll learn what that is later. And a new one for you probably is AQ, meaning dissolved in water. So Anton Lavoisier studied this. He was the father of modern chemistry, and he was very influential in the movement forward of the sciences, moving out of the more religious part of history that controlled science and philosophy to the more scientific part. So atoms cannot be created nor destroyed. So the number and kinds of atoms that enter a reaction must be the same as the number of kinds and atoms that exit the reaction. So we had 2 hydrogens. So this is H2. There's 2 of them. Here's my 2 H2s. So that means 1, 2, 3, 4 atoms of hydrogen in the reactant side. So this 2 times 2 is 4 atoms of hydrogen in the reactant side. And then 1, 2, 3, 4 atoms of hydrogen on the product side also. 2 times 2 like that. Oxygen, we have O2. So that's 1, 2 oxygens on the reactant side. And they have 2 times 1, 2 oxygens on the product side. So this is what we mean. You have to be able to count the number of atoms on the reactant side and have it equal to the count of the number of atoms on the product side. So here's my hints on balancing. Make sure all formulas are written correctly. especially if you're beginning with a word equation, only alter the coefficients. So we can't ever change the subscripts or change how the compounds actually occur in nature. The yield sign, or the arrow in between, represents an equal sign between the reactants and the products. We'll begin with the largest compound. Also, the coefficients must be in the lowest terms. So if you multiply across the top and you get 2, 4, and 2 for your coefficients, you would have to reduce those down to 1, 2, 1. Leave oxygen and hydrogen for last. That's why the reason we do this is because oxygen and hydrogen occur in a lot of different compounds. So we're going to leave those for last because they usually fall into place on their own. Sometimes you might need to think of water as HOH instead of H2O if you're dealing with a double displacement reaction and you have the polyatomic ion OH. If an atom's present on one side of the equation is an odd quantity and the other side of the equation is an even quantity, try doubling the odd value. Some equations or even some compounds have an element present in more than one compound or a part of the compound. Be sure to combine these. Next, it says, remember diatomics. Well, I have another video on that, but I'm going to summarize it for you. So, Janine rule or Brinkelhoff. Brinkelhoff is bromine, iodine, chlorine, fluorine. Those are our INE elements. And then GEN would be oxygen, nitrogen, and hydrogen. So that's where this Janine molecule rule comes in. And this is what Brinkelhoff means, is the symbols for the elements. What this means is these particular 7 elements do not come by themselves. They always come in pairs. Like such. So these molecules, if you see them written as words, are going to come in pairs. So when you see bromine liquid, you say Br2. Iodine solid is I2. Chlorine gas is Cl2, so on and so forth. All right, let's practice first how to count the atoms. So this is called the T-chart method. In the T-chart method, I figure out what elements are involved and I list them in the center here. So manganese, oxygen, hydrogen, and chlorine. You'll notice that the elements on the reactant side have to occur in the product side also. So then we count them. Remember that manganese here, MnO2, has no coefficient, therefore it's 1. So 1 manganese and 2 oxygens on the reactant side. I'm going to list them. See, I put reactant here, and then I'm going to just count the number of atoms. 1 for manganese, 2 for oxygen, 4 hydrogens, and 4 chlorines. So I'm just going to list them. I have 1 manganese here. Now, chlorine, you have to be careful here because I have 2 in this compound, but I also have 2 in this compound. So I have to add those together for 4. So I have 4 chlorines. Water has 2 times 2 or 4 and 2 times 1 or 2 oxygens. When you add them all up, the numbers here have to be the same as the numbers here. If they are, you say it's balanced. All right, for this one, I'm going to do this off to the side so you can see what the problem would look like beforehand and how we would construct a T-chart. So this is what a problem would look like. NH4, so ammonium sulfate plus sodium hydroxide yields ammonia plus water plus sodium sulfate. Remember, we used our rules that we learned in naming that sodium sulfate has a charge of -2, so it has to have 2 sodiums. So that's where those numbers come from. So when I'm given a problem like this, I'll write it off to the side, and then I just start to list the elements that are present. So I go from the beginning, and I say, what do I got here? I've got some nitrogen, hydrogen, sulfur, oxygen, sodium, and I already have oxygen and hydrogen listed. Let's double check. Nitrogen, hydrogen, oxygen, sodium, sulfur. Okay, we're good. Now I'm going to go through and count. Remember, this subscript here means that I have 2 ammonium ions. So it's actually NH4 and NH4, like such. So this multiplies here too. So I have starting with 2 nitrogens and 8 hydrogens. But I also have to pay attention to the fact that I have a hydrogen here. So this is going to be 8 plus 1 or 9. Then I have 1 sulfur. I have 4 oxygens here, but I also have an oxygen here for 5 and 1 sodium. Let's do the same thing for the other side. Before I begin, I have 1 nitrogen. I have 3, 4, 5 hydrogens. I have 1 plus 4 or 5 oxygens, 2 sodiums, and 1 sulfur. Now remember our rules that we really want to leave oxygen and hydrogen for last. So you can start with the largest compound, which is this ammonium sulfate, and let's start to balance. I want to start with nitrogen because I'm going to leave oxygen and hydrogen for last. Sulfur's already balanced, so I'm going to put a 2 here. When I put a 2 there, that changes my nitrogen, but I have to be careful because it also changes my hydrogen. Now, don't get tricked into saying, well, I put a 2 in there, so I've doubled the amount of hydrogen. I have double the amount of hydrogen only in this compound. So it's 2 times 3, or 6, 7, 8 now. So now my nitrogens is balanced. Let's go over here and balance my sodium. My sodium I'm going to balance by putting a 2 there. Now my sodium's balanced. But that also changes my oxygen and hydrogen. So right now, let's add this up again. 4 oxygens here, 5, 6 oxygens. Let's go to hydrogen. 8, 9, 10 hydrogens now, like such. Okay, let's reevaluate. My nitrogens are balanced, my sulfurs are balanced, my sodium's balanced. The only thing that's off is hydrogen and oxygen. So let's go through and let's balance those. Well, if I put a 2 here, that gives me 6 hydrogens, 7, 8, 9, 10. And then it also changed my oxygen, so I have 4, 5, 6 oxygens on the products, so I am balanced. So my final answer would be as follows. Okay, the other thing you can do is balance by inspection. Let's say you didn't want to do a T-chart. In this case, the T-chart would be kind of easy. So my problem to start with was like this. So when you get better at this, you're going to look at this and be like, I can do this without even doing the work of a T-chart, because I need to start with the trickiest one, which is aluminum oxide, and just put a 2, a 3, and a 3 here. So you can usually do this by inspection. So if I did a T-chart, it would look like this. And then I would go through and put a 2 here, a 3 here, and then a 3 here. So you can recognize I can do this by T-chart method, but otherwise, if I look at it and say, I think this is straightforward enough that I can do without the T-chart, you can also do that too. That's called balancing by inspection. Now, your turn for the rest of the chemical reactions that are in the notes. It is your turn to balance the rest.